So this is my first time in your country, so it's very exciting for me. Thank you for inviting me. So the idea of this talk is to use ideas from topology to study a very difficult problem in analysis. And in fact, this problem is so difficult that probably you want to take the point of view that you either try to get some understanding of the problem or change the problem. You don't have to solve a problem. You can change the problem. In fact, when you do mathematics, you go towards some problem, but you usually take whatever you find. So you don't usually solve the problem anyway. And so this problem is it's in 3 dimensions, and it's about understanding the motion of fluids in 3 dimensions. And I'm going to consider the case when the fluid, when it moves along, it distorts the space, but the volume is preserved. So volume preserving. And we suppose the fluid is subject to Newton's laws. And then there's a model, sort of what you might call the continuum model, for the evolution of such volume. This is also called incompressible. Like water. And there's a continuum model, a partial differential equation, which we'll get around to later, which a very elegant equation. You have time derivative on the left, and then you have a nonlinear quadratic term, and then a couple of linear terms. Well, let's say one linear term involving the friction. And a lot of people have studied this from the 30s. Well, they've studied it in previous centuries, but the modern analysis studies emanate from the 30s with work of Leray in France. And there's a famous paper by Kolmogorov, K41 it's called, about how the nonlinear term allows the different scales to interact. Come in. You shouldn't be late, to lectures. Because the only chance you have to understand something in a lecture is in the first few minutes. So I learned that as a young man. And then after 5 minutes, leave early, but don't, come early, leave early. Yeah, all right. Anyway, so I forgot what I was saying about this. Anyway, in this problem, so it turns out in 2 dimensions, the theoretical problem has been solved. The practical problem of computing has not been solved. And in 3 dimensions, the theoretical problem has not been solved, and the practical problem, of course, of computing has not been solved. So, okay, so now there's an idea about this model. I could write a formula and all that, but it has a name, a Navier-Stokes equation. So this equation, so it's a very precise math problem, which is nice for mathematicians. It's studied a lot by theoretical mathematicians, and progress has been very minimal in some sense. even since the 30s. There have been a few technical things here and there. Well, this might be an exaggeration, but not much has happened about this equation in dimension 3D. Although in dimension 2D, I think there's a very optimal discussion. In fact, I forgot the name. There's a Russian mathematician, Udovich, perhaps is his name? Udovich, I think. He and also a group in the West got the maximal result. But anyways, huh?
In 2 dimensions.
In 2 dimensions, yeah, right. But again, I say it's a theoretical result, and it's not very easy to compute. And computations that are done are kind of paradoxical because they reveal things that the mathematics suggests shouldn't be true. But anyway, let's see. So now it's been studied a lot from the theoretical point of view, and of course it's studied a lot from the practical point of view. Engineers and physicists and applied mathematicians use this equation all the time. I didn't write it down, but they use this equation to model things and build airplanes and relate to experiment and study flows in reservoirs, oil fields. So it's an extremely useful equation, but the theory of it is lacking, as I've said. So now the equation is not, I repeat the words of an expert, it's not a fundamental equation. It's derived from kind of, you make a particle description, a Boltzmann statistical physics description. You make certain assumptions about thermodynamic equilibrium happening fast enough, and then you kind of pass to the infinitesimal form, and you get an equation. So it's derived from some other considerations. But it's a very beautiful equation, and the mathematicians love this equation. Okay, so and it's only derived, it's not even rigorously derived from the more fundamental principles. You have to assume certain statistical events happen, certain ergodicity happen and things like that. So, but they're true. I mean, you know, this room, the air in the room, you blow, and then it does a little bit, and then it equals, it works. Thermodynamics works. So it's not a problem with these assumptions, but theoretically it's a problem. So, so on the plane coming here yesterday, or yet whenever it was, this word came up. So, emergent phenomenon. So, in other words, this equation, so to speak, emerges from a more fundamental point of view, like particles and so on. And so the goal today, in fact, I wrote that down. See, I'm going to write down the goal now. You know, so this, I don't know, is this word emergent, is the English level here up to the level of this word? This is an interesting word. It's a kind of it's a word that's used a lot now in the highest levels of science in the United States, because there's many systems, like our consciousness is some emergent phenomenon of all the little nerve cells in our brains and so on. Thermodynamics is an emergent phenomenon. All sorts of complex behavior has patterns that emerge from some more. So it's a nice, kind of a cool word. So, and it occurred to me that what I've been trying to do is actually can be described by this word, so I'll say it that way. So the goal is to, here's the goal. Let's see, is this, that's okay to do it like that? 2 blackboard, okay, good. Good, so the goal, right here, is to or cause or derive, let's call this NS. Cause the NS PDE model of incompressible fluid motion in 3D to emerge from an explicit system of finite dimensional systems. So, just a little aside, when you look at the analysis when you try to study this equation, I mean, this is a truism and a banality. The difficulty arises from the nonlinear term and the fact that in the continuum model you have infinitely many scales, and the nonlinear term potentially allows all these scales to talk to each other, and it's hard to control what happens as you evolve in time. And this just disappears in a finite dimensional model. A huge aspect of the difficulty. So if you have finite dimensional systems, and finite dimensional systems or models, we'll call it models, and they should be defined by analogous physics or physics or considerations. Okay, now let's put that goal up here. Okay. Okay, that's our goal. And then, that's the goal of this lecture. And then, when you have this goal, then you can work on these finite dimensional models and try to prove that in certain settings, the solutions of the finite, well, do two things. The finite dimensional models are easier to analyze because this infinite dimensional problem has been reduced, and also there's a vast theory of finite dimensional dynamics. I mean, I've spent a couple of decades in this field, so I'm kind of aware of many of the things there. And people like Kolmogorov students, Sinai, and then in the West, Ruel and Bowen, all the people in geometric dynamics. Anyway, finite dimensional, a lot of things can be brought to bear on finite dimensional models. Chaos theory and statistics, the ergodic theorem. So you have a lot of things. So if you have finite dimensional models, you can sort of treat them powerfully, a priori, where you can't do that in infinite dimensions. In fact, that's why I went into this field. I said, I know all about dynamical systems. I'm going to try this dynamical system. But it's infinite dimensional, so all bets are off from the beginning. You can't use many of the techniques. So let's go backwards. Let's make the thing emerge from a system of finite dimensional models. Then we have the option of using that powerful theory on the one hand. But we don't actually know what the outcome is going to be about this continuum model. It's just a model, so you don't really, it's not like the Holy Grail. Holy Grail. Is there a Holy Grail in the Orthodox Church? The Holy Grail, yeah, okay. I mean, in PDE, this is kind of like a Holy Grail problem, but it's not. I mean, the real problem is to understand fluids and have models. And as I mentioned, even in 2D, where the theory of the model is okay, the computation of the model is not okay. So you'd really, independent of whether you have the theory, you want to be able to have things you can compute and use. So there's another. So I mentioned you can try to change the problem. Another way to change the problem is to say, well, let's don't. In fact, this is a very comforting point of view. You change the problem like this, and in this change problem, you don't have to prove anything. It's very interesting to have a problem in math where you don't have to prove anything. And in other words, if you could just find a way to make finite dimensional models, which when you put on a computer gave nice results, that would be useful. So you don't prove anything because maybe this equation doesn't even have a good solution. Maybe it blows up. So, yes?
Fly with that practical applications.
What?
Airbus.
What? Air good? What?
No.
I have hearing problem. What?
Okay. Airbus means this, how to say, airplane.
Oh, yeah.
Airbus.
Airbus.
Will it fly with that, how to say, finite dimensional solution and so on?
Right. They use all the time, yeah?
They use all the time.
Yeah. Okay, yeah. I'm going to address that point. So, yeah. I mean, in fact, there's a famous Russian Galerkin. The Galerkin approximations, you can take any very general system and you just sort of project, you think of it as a vector field on Hilbert space, and you project in any finite dimension and sequence of finite dimensions, you get a system of projections, you get a system of finite dimensional approximations that converge to the original problem. So you can just study those directly. It's not exactly explicit. I put this word explicit in there, and I'll say what I mean. So you have a nonlinear equation. I don't know if can I talk about Galerkin approximations, and that fits with, do you know that, a Galerkin approximation? No, but I mean, you said Airbus, right?
Yes, because I know from a person who is doing Airbus,
Yeah.
Kuleshov,
Yeah.
that he used Navier-Stokes equation,
Yes.
let's say for 10 years maybe,
Right.
his institute and so on.
Right. Yeah, so let me just explain something about that. See, so you imagine, for example, anything you write down, so the fluid is determined by a velocity field in 3 space, that's its state, and then it evolves in time according to this PDE. Well, if we think of, I'm going to think of space as just, I'm going to work with a big unit cube, take a big space like this, and I'm going to make it periodic, use periodic boundary conditions, and then I'm going to divide it up into little cubes, and so on, and then make models at each level of division. But anyway, in fact, this goes back to Reynolds, where you, where he considered averages. You take your velocity field, you replace it at in every cube by the average velocity, and then you try to work with those average quantities. So another way is to think of Fourier series. So here's the 0 component, 1, 2, 3, minus 1, minus 2, minus 3. The Fourier series for each component of the velocity. This goes on forever, and then you could just, if you're working on the Airbus or something, or in a computer, you can just truncate the Fourier series at some level, let's say between minus 20 and plus 20. And then you just work all the time with this. So, so call this map that goes to here. So call the whole thing x, that's the entire thing, and this map x bar that just takes the finitely many terms of the Fourier series. And then, and then you have an equation. X dot is some nonlinear term. Maybe it looks like x dx plus a linear term. Well, you can just take bar of the whole equation. Now, the linear term, this commutes with bar, so this is x dx bar plus Lx bar. Differentiation is linear operation, and so the equation becomes this. And then you make the ansatz. You just say this is equal to, it's not true, this, and d is a linear operation, so this commutes with bar. So you just work with this equation. So there are infinitely many explicit finite dimensional approximations. So that does the goal. is trivial. That's what they do all the time. You just take your problem and you discretize it. No problem. Now, but, of course, this is not equal to this. This is not equal. So this is a basic structural thing that you know, when you take some kind of expectation, then this is not there's minus the expectation of the product. This is an interesting quantity. Statistics is about studying these quantities. This is the first invariant, and then you have higher order invariant. There's a whole infinite sequence of cumulants like this, which is the theory of statistics. And so this is kind of all, you can try to put this back in and you get actually a certain infinite sequence of equations, but then you're back to the infinite problem again. If you take in this account and derive the corresponding equations, that's due to Hopf, Eberhard Hopf, those equations. Anyway, now so I'm going to try to, there's going to be one detail in this discussion which differs from this discussion, which is the following. Let's see. Go over here. I mean, we'll see in a minute that the Navier-Stokes equation has approximately this form here. This is the form it has. There's this, and this is the big daddy term here. This is the main term, the nonlinear term. It causes all the difficulties and all the interest and creates all the interesting phenomenon. And this is a sort of brutal treatment of it. This is very brutal to do this. And this has the following mathematical consequence. That so you can define, you can so to speak define a new multiplication. Whoops, I have to wait a little bit, I guess. Multiplication. Let's define x times y at the level of the bar. Well, let's define a new multiplication to be equal to x bar times y bar. So you have some way of averaging out or truncating the Fourier series, and then you define this. And sorry, that's not what I mean. A new multiplication on the x bar level. So it's going to be x bar times y bar. So a truncated system can be extended by 0 to an actual system, and then you just multiply the actual systems and then take the bar. So this is going to be like a definition. And so in effect, what you've done is you've taken, so this equation that you're using is taking the same equation where this multiplication is the key term that creates the nonlinearity. You're taking a new multiplication called the bar multiplication, which is defined by this. So you're replacing your objects by the approximate objects, and then you're defining the new multiplication to be this, and then you're writing the same equation. So it's the same equation, but with a new multiplication. Now, that looks pretty good. In fact, this is what we do when we multiply real numbers. In a computer, we take them out so far, so many decimal places, then we multiply, and then we throw away we go back to 100 digits or whatever we're using. Now, it's very shocking actually, but one night I was lying awake most of the night worrying about this fact. This multiplication of real numbers that you do on a computer is not associative. It's commutative, but it's not associative. It's commutative but not associative. So we don't actually have a practical way to multiply real numbers which is associative. You know, we think about, we have associative multiplication, we don't have it. And I was worrying about, do we really not have it? And you know, and I was trying to think about how can you multiply real numbers and have associative multiplication, really, you know?
This way the error accumulates.
The error can accumulate, right. It's not associative, there's an error. And so, you know, what do you do with it? You forget about it or you deal with it? That's what's happening here. You're just ignoring, oh, so this new multiplication is commutative, but not associative. Okay. So, so what does it mean, what we're doing, you know, we're on computers and stuff, what does it even mean? And then I started thinking, well, I think about 3 in the morning, I said, well, let's just replace numbers by fractions, rational numbers. Then we can multiply them exactly. And that works. And then I thought, oh, well, that's not really too good either, because you start multiplying lots of integers together many times, they get very long, so they get outside the computer. And I said, oh, well, they're fractions, so you can reduce them. But then in order to reduce them, you have to factor numbers, and that's an intractable problem. So then I got upset again and still couldn't sleep. Anyway, so I don't even know how to multiply real numbers. So, but anyway, in numerical analysis, I believe, at least I know one group in France, they're basically doing this. They're taking some bar operation to be able to put it in a computer, and then they're just defining a new multiplication on the bar operators by this. You can embed the systems back in the full system easily, and then you just multiply them in the full system, but then you take bar again. And so the statistics, you know, these errors are sort of built in, maybe. So, so the whole point of making you listen to me about this, when it's very analogous to what this gentleman was suggesting, is that I'm going to be doing something like this, but when I go to this level here, my multiplication will be associative. But it won't be commutative, but it will be associative. So that's, in a nutshell, that's the main point. And the reason that we can do this is because we have some constructions in algebraic topology which produce associative and non-commutative multiplications, which fit with this discussion. Okay, so that's so let me kind of write that as part of the goal. So we will, let me see, I'll do that here. So or this is also called combinatorial. So this is two-part talk. We take a break after 50 minutes. Is that right? So you just tell me when to break, okay? Algebraic or combinatorial topology. To effectively do something like this, but this dot here that we're going to use, this will be at the level of combinatorial topology, like averaging over cubes, and then we're going to multiply via algebraic topology and get an associative multiplication, but not commutative. So it's a little like quantum, non-commutative but still associative. Algebraic combinatorial topology via their associative products. So in a nutshell, that's all. I mean, you can leave now. This is the point. But, yeah.
So is it supposed to be strictly associative?
It's strictly associative. Strictly associative, right? Exactly. And we say on the nose.
Okay,
On the nose. On the nose. Means it's equal on the nose, not just sort of equal. Right, on the nose. Okay. All right, let me put this back up again. Yeah. Okay. So really, we can. This is sort of the motivation. Let me give a slightly more general motivation. This is the real motivation, but then there's a broader motivation. As you would like to do, we'd like to also do the same thing with differential geometry. So on a manifold, we have the various fields, like the differential forms and various operations, and we would like to have finite dimensional models of those. And again, there's the issue of the nonlinear term is important. And now let me just remind you about differential forms. Let's see. Suppose I'm I'm on the plane R2, and I have a one form, so I have something like dx, phi of x and y, dx. So I could have plus something times dy. Let me put. Okay, now the following, you've got a function here. It has two partial derivatives. So to control this function, you really have to control both of its partial derivatives. But now, if you're doing Stokes' theorem, which in this problem with fluids, when you do the physics, you sort of always use things like what comes in and what goes out, and you use Stokes' theorem. Stokes' theorem only involves the operator exterior d, which is some combination of the partial derivatives. So let's just look at that a second. I'm going to suppress this term. Just look at one term. So this is phi sub x dx plus phi sub y. Well, this is equal to d phi times dx. I'm doing the calculus of differential form. D phi is phi sub x dx plus phi sub y dy. So you put that in, dx, and dx times dx is 0. And so you just get phi sub y dy dx, which is minus phi sub y dx dy. So if you just look at exterior d of this thing, you just pick up the y partial. The other partial goes away, and on this term you would pick up the x partial, right? So you only pick up some of it. Now there's a star operator, there's this Hodge star operator, which will, star of dx is equal to dy. So star of phi dx is equal to phi dy. And so then if you take d of star, let me call this thing eta. This whole thing here is called eta. So this is d eta. Then, well, now the star of this is just rotates dx into dy. Star does that. And so d phi now is going to be phi sub x dx dy. So, right. And so, d of phi dx. So d of star eta is, so you see, if you know d and you know star, if you know these two operators, then you have complete control of what goes on. You don't have to think of the partials, which are depend on coordinates. So this is sort of a conceptual way to have coordinates. So this is well known. So if you're just an analyst and you're trying to control things, if you can control this and the composition, then you can control everything. Okay, that's one thing. That's basic to what's called elliptic PDE. They use the Laplacian to control all the derivatives. Powers of Laplacian, if you can control that, then you can control all the higher derivatives. It's called elliptic theory. Okay. Anyway, so then the other thing is the multiplication of differential forms, which is called the wedge product. So this is the wedge product. This is what I've been discussing. Let's see, this is wedge. So you write eta wedge nu, for example. So I did it here. You just multiply them together and use the rules. They anti-commute, and dx times dx is 0. That defines the rules of multiplication. And that's this fantastically beautiful algebraic construction called the Grossman algebra. And so you have this beautiful Grossman algebra of differential forms. This is a derivation. Then you have this sort of mysterious involution or order 4 operator here, depending on the dimension. In 3, it's an involution. And you can think that if you write a partial differential equation and you use coordinates to write it out, and you use a metric and everything, and if it's coordinate independent, namely if you rotate coordinates, you sort of have a meaningful equation. That's sort of, not completely, but usually it means you could write it out in terms of these 3 symbols. So differential equations that can be written out in terms of these 3 operations are sort of the natural equations that these ideas, if they have any value, are applicable to which these ideas are applicable. Okay. Now, how are we doing on time? 10 more minutes?
Yeah, exactly.
Okay, fine. So then, to generalize, so the more general goal so the Navier-Stokes equation is such an equation. You could write it out in terms of these 3 operations, okay? The continuum model. So generalized goal is to do the same for D star and the wedge product. So to make explicit finite dimensional models for this system, and I will want my explicit versions of this to be strictly associative, but they won't be commutative.
We can suppose to be the wedge.
The wedge, yeah. The wedge is commutative, but this is at the continuum limit. I want to go to the finite limit, finite approximation, the bar level. All right. Same for this, which means reading, we want this structure to emerge, use that cool word again, emerge, from an explicit system of finite dimensional models. Okay? That's what we want. So then, it's like going into the basement. You know, we're up in this building here, but I don't really know what this building is about. If I go down in the basement, I can look at it better. Dirty down there, not as pretty, but I'll understand it better. So this is going into the basement. Make it emerge from something more fundamental. And this is actually what statistical physics does. The Navier-Stokes equation does emerge from statistical physics, but only heuristically. It's not theoretically derived. And when I was first studying this problem about 20 years ago, I wanted to find, why is this problem so hard? I was astonished. I went to a physics lecture at IHES in Paris, and I said, they don't know the Navier-Stokes equation? I mean, they use it to build airplanes and everything. You know, they use it everywhere. How could they not know? There's billion-dollar engineering industry going on all the time, and how can they not know it? And it's just that mathematics is not always connected to reality. For example, in dimension 2, I've mentioned, even though the mathematics has been done, the practical computation is not done. So that's another And I tried to find out why it hasn't been solved by these great analysts. And you could find out why. I won't want to go into that. But then other interviews I had with experts revealed that that if they actually understood more about the basement, namely the kinetic theory, the Boltzmann theory, the statistical theory, they claimed, in fact, you won't make progress on this derived equation until you make progress in the basement. So, well, they haven't made that progress. So I'm suggesting we'll make a new basement, a mathematical basement instead of a physics basement. All right.
Would you write out the Navier-Stokes equation?
I won't yet.
In those terms? Not yet?
I will eventually, not yet, even for you. Because I have a plan. Okay. If we go outside and smoke, I'll show you on a small piece of paper. All right. No, it's just because the reason I didn't want to do it is I wanted to show you how that term is derived, because we're going to, in other words, we can make sense of that term even in our setting. So we want to show how that term is derived, and then I'll write the term, and then I'll write the corresponding term here. That's the way I'm going to do it, rather than just put down something that we won't understand anyway. I mean, it's very pretty, but I mean, this is incredibly beautiful stuff, this calculus. It's seductive, séduisant. All right, so let's go. Okay, so now I want to start just to mention the goal. So now, okay, so we actually have to. We have our fields. Well, every time I raise,
You can press harder.
use a dry one.
No, press harder, yeah.
Oh, I know, but. Let me put it over here. So we have our fields, the forms, and we have these operations on them. And we want to discretize this package, right? Okay, so this and this, we have a well-known, beautiful solution. Beautiful, well-known solution. It is called algebraic topology. Namely, we can, and so what I'm going to do in this talk is, I'm going to use my hand. I think that's better. So I'm going to start with this unit piece of space. I'm going to put periodic considerations, so it's really a three-dimensional torus. But then I just draw it like this, and then we're just going to start subdividing it into cut everything in half. So nice pictures here. Anyway, the big cube breaks up into 8 cubes. And then we'll do it again. And actually, to simplify matters, I mean, I'm going to come back to this cube, but I'll kind of indicate it. So I'm actually going to start subdividing like this and like this. Standard cubical grid stuff, right? And then what we can do is we have our eta. Well, eta might be a 1 form, something dx plus something dy, or it might be a 2 form. I'm doing it as if I'm in the plane, but I'm going to have dx dy dz, and then dx dy dy dz, and dx dz, and then dx dy dz. In general, and then function. So 1, 3, 3, 1. Here I just have 1, 2, 1. And And then these are functions, function coefficients. And then what we're going to do is form what's called the associated cochain at each level. So form averages. And these are called cochains at each level. So we take our one form here, eta, and then we can integrate it on this edge. And we have to have a direction. So we integrate this form against a direction, we get a number. If we change the direction, the number changes to a minus sign. And then we integrate here, we integrate here, we integrate here. Integrate here, 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 here. It doesn't matter how you choose the arrows, because if you change the arrow, it changes by a minus sign. So the definition of it, and that's called a cochain in algebraic topology. It means it assigns to each oriented piece a number, so that when you change the direction, you get minus the number. And then this is actually, we got one at every level. So we get something here, a cochain, and then we get the averages here, and we get the averages here. And they satisfy the following consistency condition. The number here, if we have numbers assigned to all of these, we can get numbers assigned to the bigger ones just by adding these numbers. So this is the natural way. If you have a cochain at this level, you get a cochain at this level just by averaging. And then at this level, just by averaging. So when you integrate a differential form, you get a consistent system of cochains at every level. So that's the first discretization, well-known, very beautiful discretization of the field. And clearly, if this form has continuous coefficients, this system of cochains determines the form. Because eventually, when you're integrating over a tiny little piece, the form is essentially constant. So it's just the length of the piece times the value. So the form is encoded in here. So I can erase the form. I have it in here, in this explicit system of finite dimensional models. And these are finite dimensional because I've made it periodic. So there's just finitely many pieces at each level. Okay, we're trying to discretize this. So we can integrate our forms, and so I'm going to erase this now because we're trying to have the continuum objects emerge from the finite dimensional objects. So the finite dimensional objects then is a cochain at each level and a consistency condition that when you add the values here, you get the value here. So we forget differential forms, but the differential form gives such a thing. And it's easy to show that they're dense. Differential forms, there's a natural topology here. This is an inverse system of finite dimensional vector spaces, so we can form the inverse limit space, and the differential forms are dense in there. So there's a certain dense subset in there, depending on the kind of regularity assumptions you make. But let's just think the differential forms are there, but let's just think these are the primary objects. I'm going to call this thing C, which is the inverse limit of all the cochains at each level. So this is like alpha, alpha prime, alpha double prime. And Ludwig just mentioned this is like renormalization. When you take something here and you average, it's like the renormalization group. Yeah. Okay. Okay, we have that. And then, so this emerges, so to speak, is some interesting subset of this. It's a dense subset, some interesting subset. Okay. Then this one is also natural because in algebraic topology, if you have like something defined on every edge, then you can get something defined on every face by adding up around the boundary. So this value plus this value plus this value plus this value, I'll add to that. That'll be that value. And that'll, if if this is called C, all these values, then the value that you put here is called the co-boundary of C. So this is the co-boundary operator of algebraic topology. So on a cube, if you have something in dimension 2, you add up all the 6 values on the faces of the cube. That's what you put on the inside. That's the co-boundary. That gives you a 3-dimensional cochain from a 2-dimensional cochain. And then, of course, if you have a function with something defined on the edges, then you just take this value minus this value, and that's like df. That's an obvious approximation to df. So you have the co-boundary operator. So this is a system of cochains, the cochain system of cochains, and this is the co-boundary. And of course, Stokes' theorem says that if you average if you average on the boundary, then that, and then you take d of the form and average on the interior, that's consistent with this. That's Stokes' theorem. So Stokes' theorem says that this system of cochains with the co-boundary operator is exactly a correct discretization of these 2 parts of the structure. Okay, now this one, thanks to Poincaré, we also have, although there's a little bit of you have to sort of think ahead a little bit, but basically it's the dual cell. In fact, this is how I found this stuff. I want to draw this picture because this step is actually completely general. For any partition of space into cells, there's the famous dual cell decomposition. So you can form the dual cell decomposition. And this is how you prove Poincaré duality, because when you're computing the co-boundary operator with respect to the triangles, it turns out you're computing the adjoint operator with respect to the hexagons. And that gives you, in the complementary dimension, there's an operator called the Poincaré dual operator. It takes, like, where's one of my triangles? Here's a triangle. Like this edge here is going to, in the original decomposition, is going to correspond to this edge in the dual decomposition. And if you were in dimension 3, an edge in one would correspond to a dual face in the other. So, and this converts the co-boundary operator into the adjoint of the co-boundary operator, called the boundary operator. And so this, we sort of know what star is going to be, although there is a nuance, because star takes you from one system to the dual system. It doesn't take you from the system to itself, so we have to adjust that. But now let's get back to the main character. Well, both of these are main characters, but this is sort of, this one we know we can do something with using algebraic topology. We know a priori. Not so clear a priori that we can deal with both of them simultaneously. Okay, but so how do we do that? Well, so one of the fundamentals of the Poincaré duality, one of the fundamentals of algebraic topology, is that when you compute using a cell decomposition, like something like homology or cohomology, if you subdivide, you get the same computation. So that Poincaré knew that. Poincaré knew that when you subdivided, you get the same computation. So Euler knew that for the Euler characteristic, right? In fact, I must say, my wife has this book about Euler, and I was reading it a few months ago, and all about this institute and him being here and having all these kids and writing papers up until the last, in his 80s, and he'd have a kid on his lap reading to him, and he would be dictating, and another kid would be writing. And then I got interested in this trip. Before that, I was interested, like go to Russia and all that, but that, I don't know, somehow. Anyway, the Euler characteristic was the first thing that was known to be independent of subdivision. And this entire computation is independent of subdivision. And you see when you, so there's a common subdivision here, which is this thing. See, that's a you can amalgamate these are kites. They look like these things you fly, kites, right? The kite subdivision, if you amalgamate it this way, you get the hexagons. If you amalgamate it this way, you get the pentagon. So there are two different amalgamations give you the two dual things. So each one computes the same thing, but computing homology in one computes cohomology in the other, and so that's Poincare duality, right? So anyway, so now I was looking at this, and this has a sort of combinatorial description that's going to tell us how to do this product. So the idea is, what is a kite? It's not this or this, but it's the common subdivision I'm going to concentrate on. This cell here, so let's take the original triangle, for example. I have 7 cells, 3 vertices, 3 edges, and 1 face, right? And I have an inclusion relation. This is contained in this, this is contained in this, this is contained in this, this is contained in this. And it turns out that this kite subdivision is exactly the sort of graphical realization of that partially ordered set. In other words, you have a partially ordered set, you have 7 things, and it's partial ordered by inclusion. And if you take the sort of graphical realization of that, you get this kite subdivision. Namely, you consider pairs A, B, where A is contained in B, where A and B are one of the original 7 cells. Then this cell contained in this cell corresponds to that piece. This cell contained in this cell corresponds to that piece. This cell contained in this cell corresponds to that piece. This cell contained in this cell corresponds to that piece. This cell contained in that cell corresponds to that piece. And then this cell contained in the whole thing corresponds to that piece. This cell contained in that piece, this piece, this. So every one of these pieces of the kite subdivision is just corresponds to the partially ordered set of inclusion. Now, when we do this with cubes, the dual decomposition for the cubical thing is also the cubical thing. This is the dual. So when you intersect the dual with the original thing, you just get the standard next stage. So that's this remark, if you read my abstract, it says if you subdivide the cubical division, the cells of the next subdivision are labeled by ordered pairs of cells of the coarser subdivision, ordered where a pair is allowed if one's contained in the other. And then you could define a product, first a partially defined semigroup by a pair AB times a pair, and let me just mark. The dimension of this cell corresponding to a pair is the codimension here. So this edge contained in this is codimension 1. So it corresponds to a 1 cell. This vertex contained in the face, that's codimension 2. It corresponds to this 2 cell. So it's the codimension. So the dimension of the cell corresponding to a pair is the codimension. And I'm going to define a new operation. This times this is just AC if and only if B equals B prime. So if B equals B prime, I'm going to define this times this to be that. That's going to be the operation, okay? And I won't define it otherwise. And then if I take linear combinations of these pairs, I'm going to define an algebra by, on the generators, I'll use this rule, and if B is not equal to B prime, the product is 0. That's going to be my associative algebra. So it's extremely simple. So as soon as you subdivide, the cochains becomes an associative algebra. And this is consistent with the coboundary operator, and it's consistent with algebraic topology. This is a correct notion of the topologist cup product, which is supposed to be an approximation to the wedge. Okay, so that's my associative algebra in a nutshell.
That style is different from that.
The two cells are different.
Excuse me?
Star up is the same as.
No, I haven't discussed star yet. I'm discussing.
Bad notation, there are
No,
two stars.
notation.
It says if
It should be-
star-
Oh, yeah.
Star is a bad, yeah, put some dot.
Just put a dot. Good, thank you, yeah. Yeah. Actually, never mind. What?
You could put copy.
I don't want to put cup. Well, okay, I can put cup. Okay, I can put cup. Anyway, it's a completely canonical. But the first subdivision does not have this product. The second, you have to subdivide once, and then the relationship to the first subdivision tells you how to make the product. So there's some additional combinatorial structure. So at each level, not the first, we have a product. We'll call it product 2, product 3, etc. Product n, right? Okay. These are associative products. The co-boundary operator, I won't bother showing it, but it's true. You can check it, is a derivation of this, and the induced product structure on cohomology is correct. That's a well-known thing going back to the 30s of Whitney. Any locally defined bilinear operation which is consistent with the co-boundary operator leads to the correct thing on cohomology. So it doesn't matter what you put. It doesn't even have to be associative or commutative.
Hopefully they do consist each with the other.
No.
No.
Life would be over. I mean, this problem wouldn't even be on the blackboard if that were true. Yeah. So, yeah, I was going to say that this operation is perfectly consistent with the co-boundary. In other words, if you average and take the co-boundary, that's the same as first take the co-boundary and then average. Right? But these products are not not consistent. Yeah? However, they're trying to be. They're trying to be. They want to be. I want them to be, but they're not. But everybody wants them to be. They're not. Okay, so now we want to discuss that. Oh, it's coffee. I said do this later. Okay. Okay. Yeah. So we do a few little examples. So what is this product? So let's go to dimension 3. So well. And then I subdivide them. I might have this cube here. So, the vertices of the subdivision is like AA, you know, A2, A2, A1, A1, A2, A2, A3, A3. I mean, A is contained in A, that's a vertex, right? And this is E, E, and this is F, F. F contained in F, E contained in E. So the vertices are ordered into ranks. There's degree 0, degree 1, and degree 2. So there's, in every cell of the subdivision, there's a minimal vertex and a maximal vertex. So for example, this is the minimal vertex of this 3 cell. The maximal vertex is there because this is vertex, vertex. This vertex is 3 cell, 3 cell. Okay? And now if we want to, so for example, if you want to make a triple product of cochains, let's say 1 cochains, and get the get some contribution at the volume level, or let's say first I guess I should do a binary product. Let's do 1 and 1. So a 1 cochain and a 1 cochain. So let's see if I do this face here. This again will be the minimal vertex, and this will be the maximal vertex. So this is face, face, vertex, vertex of this big cube. And now, if I want to go A less than B, B less than C, and I'm going to get AC, I'm going to have to do something like this edge. If this were an x, let's read from left to right. If this were an x, if x were 1 on this and 0 on the rest, and then y were 1 on this and 0 on the rest, then x times y would be the vertex, edge, edge, face. So the product would be vertex, face, which would be this thing. So the product of this with this is the face. It's not commutative because if I tried to do this times this, it would be in the wrong order. So that's this times this is 0. This times this is the face. So it's very non-commutative, but it is associative. And if I want to get to here, 3 things, I can go vertex, edge, edge, face, face, 3-cell. So this composition would give me a term reading dimension 3. But if you just take a random collection distributing of coefficients on x, y, and z, you look at all the possible combinations and so on and see what the product is. There are 6, if you take any one cube, there are sort of 6 ways to permute. If you take any 3 edges, there are 6 ways to permute the order. Either all products are 0 or only one of them is non-zero and all the rest are 0. So it's very picky. It has to be done just the right way. And also there's 6 appears in a second way in the sense that there are 6 ways to get this contribution out of this, because you can go like this, or you can go 3 ways for the first choice. Then if you've done the first choice, you have 2 ways. Well, it has to be like this, and then the last choice is unique. So it's 3 times 2 times 1. So you have 3 ways of having a triple product give a contribution on this cube. Anyway, so so it's something you can compute with, it's concrete. So that's what I'm going to do here. So I'm going to use this product at each level, but yet consistent. How do you say not in Russian? No is niet. How do you say not? Not consistent. Same? Yet.
Sometimes it's net, sometimes it's net. Net.
Oh, hi, Stan.
Hi.
Okay. I have this trouble, I can't really hear, so didn't hear that. All right, so that's a little practice with this product. Yeah. And then here's the niet. The maps are not consistent. And then, okay. Yeah, now let me do. Okay, so now there's a little, any questions so far with the product? So it's very well motivated. It's the natural, you look at the combinatorial structure of the kite complex. It has a natural ordering, and you just, every partially ordered set determines a semigroup, and there's an algebra there. So it's just that, nothing ingenious or anything about it. It's just lying around for you.
Who first introduced it, Dennis?
What?
Who introduced it first?
I don't know.
It's not in the reading.
No.
You?
Well, I didn't know. This question, who does something first, is not a question I like, because I often read, this is due to so-and-so. And what the person should write is, I learned about this from so-and-so's paper. And to the best of my knowledge, I don't know any other paper.
Okay.
That's what it means. It doesn't mean it's due to them. How do they know? They're not God. Anyway, so I don't know who it's due to. But, I think David Stone is aware of it, too. But I don't know. Anyway, okay, so actually being a mathematician has a lot of occupational hazard. It's harder and harder to exist in the real world because very common sense things just don't make sense to a mathematician. Like, who's it due to seems like a reasonable question, but okay. All right, so let me get back to this. Okay, so now we want to do the star operator. So, okay, so I'm just going to get to the point. Let's do the star operator. So this is how I'm going to do my product. Now I get to the star operator. Well, it has this little problem that star at one level sticks out, and it's sort of halfway. It's not at either level. So it's sort of defined at the subdivision level. And then, so you have to do something. So what I've decided is best for the time being. There's a little bit of possibilities here. Let me draw another picture of the cube. Cube. So we want to define star at the level of the subdivision. So I look at the subdivision. Let's look at just again this front cube here. Okay. And it turns out in the Navier-Stokes equation, you only need star going from 2 to 1. So to save time, I'm just going to discuss that example. Star appears twice in the equation, but 3 is the only dimension where the two appearances of star are from the same dimension, 2 to 1. So there are two kinds of faces, little faces. There are faces that are in the face of the coarser subdivision, and then there are faces that dive into the interior of the three-dimensional faces, so type 1 and type 2. So so I mean, to make it simpler, so here's a type 1 face, and then here's a type 2 face. So here, this is here and this is here. It goes in, okay? So remember, everything is based on the fact that it's not just a cubical subdivision, but it's derived from one above by dividing in half. I'm using that extra combinatorial information. I'm going to use it now here too. So then, so intuitively, this guy is tangent to this face, so it's associated to this face, and so the dual should be this thing, and so that's what I'm going to let it be. So the dual of this type 1 face is going to be this edge here. So it's going to be this edge plus this edge in the subdivision. So this is star of type 1. So it's got this plus this. This is this type 1 guy here. So normally it would be coming out of the middle, but I've translated it up to the maximal. This is the maximal vertex of this face. This is the minimal vertex. Now for this type 2 thing, this is the minimal vertex, and this is the maximal vertex. And now I'm going to take, you've got 4 choices. I want to take this thing passing through the middle and move it to one of the 4 edges because I want it to be inside the subdivision. So for these type 1 faces, I move to the maximal vertex. For type 2 faces, I move to the minimal vertex. So this is going to be the dual of the type 2 vertex. So it's like this is really part of the dual face, and this is its dual. So that's my motivation. So that's the picture for the star operator. So star of a type 1 face is here, and star of a type 2 face is here. Okay, it's going to be my definition. This is subject to change, but so far it looks, that's like what I want. Okay. All right, so now let's go to the Navier-Stokes. So now I have my language. I have star, D. I know what my fields are. And at every level I have an approximate field. At every level I have this language, star, D, and the product. Now, unfortunately, the products don't exactly fit together, but that's life. Okay, now All right, so there must be some smart way to do this with this stuff drying and so on. So goal, I want to cause the Navier-Stokes PDE to modeling to in 3D to emerge from an explicit system of finite dimensional models determined by analogous physics. Generalized goal, do the same for the language of differential forms, wedge, star, and D. Okay, so I'm going to try this language. It's perfect, except the different algebra structures don't fit together exactly, but they fit together cohomologically. So that's why we have confidence in working with it. So let's see. So I'm now going to erase this and then give it a chance to dry. And then, actually, to be smart, I should erase some of this first. So you erase two of them, and then
Do you mean that those algebra could be fit all together in a...
start over.
Do you mean that all these algebras could be fit all together in a kind of nice structure, like DG algebra, or I don't know, DG algebra, or I don't know, or you don't mean?
Well, each one is a DG algebra.
Each one. Each one.
Each one is a DG algebra. And there is a statistical theory that when you have a linear map between two algebras, like if you have a linear map from an algebra of observables to the scalars, that's called an expectation. The expectation of the product is not the product of the expectations, and there's a whole statistical theory for dealing with that. You can write all down accumulants and do statistics. And it's related to the formalism of quantum field theory. So one can imagine applying all that formalism to every one of these maps. These are like expectation maps. They're not supposed to be algebra maps. And there's a whole higher theory of cumulants. That's the way I would think about it. Well, I'm not ready to do that yet. I mean, first I'm doing more primitive things. But we know how to do that. I mean, and it fits with homotopical algebra and stuff like that we know about. So. Okay. All right. Okay, now what am I doing here? Now, okay, so now let's think about, I have Ludwig in the audience to keep me honest. He moved in here. See? Okay. So now, how do you derive the nonlinear? Let me tell you about the nonlinear term in the Navier-Stokes equation, which leads to all the difficulty and all the complicated phenomenon that it does describe. Apparently, it comes from this nonlinear term. And, and the idea is the idea for the nonlinear term is you have some body. Let me just think of it as a vague body. And you want to study the time derivative of the velocity. Well, this is incompressible, so each little piece of space has a well-defined volume. So velocity times mass is momentum. So we really want to see how the momentum is changing. So the momentum will change for two reasons. One is the particles will be subjected to some force. That gives acceleration. So d momentum dt is force. And that turns out to not be too hard to understand in this situation. And then there's viscous forces too. Those both behave in a kind of linear way. Then there's a trivial thing that you just have particles with different momentum. Like this is like your neighborhood. This is like one block in St. Petersburg. And people are moving in and out with different momentum. So you want to count how much stuff moves in and how much stuff moves out, but you measure it with the momentum, which has three components. So each component of momentum, like the x, like you have say a y component of momentum, and this particle moves, some particles with various y momentums move in, and some particles move out, and they also have y momentum. Let's think of the momentum as approximately constant. And so the number that move in minus the number of move out is the change in the y momentum in that region. So it's like a delta sub x times y, the y momentum. If we think of the velocity as x, y, z, then this is a term. And then there'll be a delta sub y times y and a delta sub z times y. So the y momentum will have three ways of changing, and there'll be a term like this. Then there'll be a similar thing for x, delta sub y of x, delta times x. This is times, delta sub z times x, delta sub x times x. And then there'll be a similar thing, Anyway, so let me write the whole thing as, so it looks like the momentum x, y, z has three components, and then you have to multiply this times all of these and add them up as vectors, this times all of these and add them up as vectors. And so you see, if you call this whole thing v, and this is sort of like delta v, this is sort of like a product v times delta v. So this total change in the momentum, because people are moving in and moving out of your neighborhood with different momentums, is a term like this. So if you pick up various books, you'll see a term like that. That's the nonlinear term. Because the momentum is acting on itself to compute its own change. And that gives you, so it's as simple as that. There's no big deal. All right, so that makes sense in any, that kind of thinking makes sense in any context. And when you write it down, so this is what Jim wanted to know, when you write this down with differential form, so v corresponds to eta, a one form, then this is the beautiful expression that's it. So see, here is the term that's roughly this term, and here's the term which is roughly this term. So eta is a one form, d of eta is a two form, star of d eta is a one form, 2 to 1. This is a one form, so 1 times 1 is 2, star of it is 1. So this is the, so then the Navier-Stokes equation is eta dot is equal to this, then there's plus the pressure term, the internal force. You know, if a lot of particles are moving in this way and fewer of them are moving out this way, there's going to be pushing this way, the pressure. So this term, and then there's the friction term, which is just some friction coefficient. It turns out you assume it's linear in response and isotropic, and so the Laplacian comes in. So you get a term like that. That's linear. And this term is nonlinear, and this term is nonlinear. But this term can be viewed in the following way. There's this Helmholtz decomposition of vector fields. Every vector field is canonically a direct sum of a gradient and a volume-preserving vector field. So if we think of this as a one form as a vector field, it has a Helmholtz decomposition. We want it to be volume-preserving because we want the change in the derivative to be volume-preserving. So this force is d of a potential. That's an exact form, or a gradient, d of something, gradient. So we add in the gradient that makes this volume-preserving. That's what this term. So the pressure, they usually write this dp, call it pressure, but it's just projecting this term onto the volume-preserving part. So it's this term projected onto the volume-preserving part. Eta is already volume-preserving. I should add that equation. I want v to be volume-preserving. That's part of the equation, which you write as d star eta equals 0. That's the volume-preserving condition. See, star is a one form. This is a two form. This is the three form. So that's really like a function. In fact, you can make it a function by doing star again, and then it's a function. That's the divergence of the vector field. That should be 0. Right. And this is, this is like the curl of the vector field.
Like it?
Huh?
Like?
It is the curl. This is the curl. It is the curl on the nose. But it's written in a different language. This is a form. So you have to sort of use various isomorphisms. Anyway, that's the Navier-Stokes equation. This term is just projecting onto the complement of exact Yeah? And then this is the Laplacian. So we'll write out at level n, we'll write the Navier-Stokes equation. You're going to write x dot, this is at level n. This is going to be our, fine, we'll use these things. So we're just going to, we'll think about this. We want to have a bilinear expression in the co-boundary and the field itself. And so I'm just going to write down the same thing. I'm going to write down my star at level n times x. X is, and then I'm going to write my product that we defined over there at level n. And then my star again. By the way, this star again goes from 2 to 1. See, this was 2, goes to 1. So this star both goes from 2 to 1. So only you have to define that star. And then co-boundary of x. And then now I'm using the metric that the natural basis of cochains is orthonormal. That's the metric I'm using. And the transpose operator is exterior D. So this condition here, the volume preserving, this is really D adjoint with respect to the metric. So this condition is the boundary of x is equal to 0. So x is a cochain, but I can think of it as a chain, and I want the boundary to be 0. So that's this condition. And then, then I project this. In each dimension, I have the Hodge decomposition, which is I have exact forms. I have co-exact, which means the image of the adjoint, plus exact, which is the image of the co-boundary, and then plus harmonic. I can ignore this. This is some finite dimensional thing. We put some normalization in to get rid of it. And so my nonlinear term is in here. And I just subtract off this component to make it be in here. So I subtract off, that's what the dt, so that's what this projection. So you project in the Hodge decomposition at the level of the chain complex. That makes perfect sense because you have a metric. You project onto the volume preserving part, which is the same thing in the continuum state. And then plus, if we want friction, we have, actually it's minus a positive coefficient times co-boundary of x, boundary of x. This is the Laplacian. The other term, which where you interchange these two, would be 0, because the Laplacian is really boundary co-boundary plus co-boundary boundary. But this term, when you apply it to x, is 0, because boundary x is 0. So Laplacian just has one term, this term here. So this is the Navier-Stokes equation at the finite level. So when do we? When are we supposed to stop?
We have like 6 minutes or so. Like
6 minutes?
Yeah.
Okay. Doesn't sound right. Oh, 6 minutes. All right. Yeah, that sounds right. Okay. All right. So now there are. Okay. So now what do you do with this? You have this system of equations. The only thing that makes it any different from Galerkin approximation or anything else is it's somehow explicit. And it's structural in the sense that you use the same structure at every level. And this multiplication is associative. So you can manipulate this equation the same way you manipulate the infinite dimensional equation with the same algebraic operations, basically, except you got to worry about star a little bit, but some of the identities hold. And you're allowed to use the associative law. So that's one good thing. So you can try proving things. You can try proving that this, now this is in a finite dimensional vector space. This is an ODE in a finite dimensional vector space. It's got this quadratic term, so it could blow up in finite time. In fact, there's a little lemma proved with Offer-Gabbard. If you just write down in finite dimensions a quadratic ODE, typically it blows up in finite time. So you need some internal energy control or something. And you can try proving the energy inequality, and you get expressions that look vaguely manageable, but you don't quite get 0 automatically. So there's still a battle going on there. But if you get some control on some energy in finite dimensions, you're happy. You've got complete control. But now, these things don't necessarily fit together. In what sense do they converge to the Navier-Stokes equation? Well, there are two theorems. And let me just call them one theorem. So type 1 is that, I'll call them inequalities imply star converges to wedge. So these multiplications as n goes to infinity. Well, let me say, no, I did want to put it this way first. Sorry. I wanted to state these theorems before certain inequalities imply that this converges. In other words, if you have two compatible systems, and the kind of inequalities you need is that as you go out here and you compare the value of a cochain here to a value of a cochain here, first of all, these things should be on scale. The values should be on the order of the size of the piece. And when you compare two values at neighboring sites, their difference should be smaller than the scale, an order of magnitude smaller than the scale, in such a way that the differences form a convergent series. So some kind of Holder condition would be enough. But anyway, under these inequalities like that, these products converge. So if you have systems that are, so to speak, continuous, then you get that. And the limit is commutative in the greatest sense. So whenever you have these inequalities, these things, they don't fit together, but the limit is defined. And the limit is automatically commutative. So it's a little like quantum things becoming classically commutative. And then 3, under more inequalities, you also need tangential inequality. You need to compare this with this value when you translate. So I call these normal inequalities and these tangential inequalities. So these are normal. And here you have normal and tangential inequalities. Inequalities imply star n converges. And so under some additional assumptions, these things converge. And this one's commutative, and then you say, hey, well, how's it related to wedge product? And the answer is it is consistent with wedge product. So the differential forms and the star operator and the d operator do emerge from this as a limit, but you need these inequalities. And then these bigger space, that's just on a dense set, this emerges, but on the bigger space, the individual finite dimensional systems are defined. That's the point with associative multiplication. So there's something, even if you can't prove things stay in this dense subset, you can still work with the finite dimensional models for computation. And if the answer is good, it's going to converge to the answer. But if the answer isn't good, it's something you have to compute anyway. That was my point at the beginning. Now do something with it. So prove something. There's one more point I can say. This is the point I like. Yeah. Stas will appreciate this. You can tell me how much better it is. See, in the continuum case, you're actually, you can control the L2 norm. That's the energy norm. All the properties of commutativity, associativity, etc., star, allows you to compute that the L2 norm is not increased, and the friction term actually makes it decrease. And some aspects of that computation goes through for this other norm. This other norm, though, is the L2 norm, or it's natural to talk about the Hilbert space of the norm on cochains. This is an orthonormal basis. So this norm is stronger than the L2 norm because it's like, if you imagine a finer and finer grid, you actually have more and more parallel lines. Let's just think of one set of lines getting closer and closer together. And so what I'm saying is these objects, if you can control, the norm that's natural here is the following norm. It's like if you're in dimension 3, you have 3 directions. It's the L2 norm on every line. And of course, if you average the L2 norm on every line, you get the L2 norm. But so you're actually controlling on every line. So how much better is that in the plane to know you're in L2 on every line with a fixed bound? That's quite a bit better than L2, right? Huh?
Yes, I think it is, but...
It's not quite as good as continuous, but it's...
Well, there is this ACL condition on a line
Yeah.
which leads to different nice properties in Sobolev.
Yeah, but I mean, but that's not a given bound on, that's not a uniform bound, is it?
No, it's not. That-
Yeah, okay. But anyway, the norm that's in play here is actually better than the L2 norm. Okay, that's the thing I like. So it's possible. You can imagine you could prove something because the norm is better. All you need is a little bit to prove this problem, but the little bit is positive. Then, if you can't do that, if one can't do that, then forget it. Then you just say, well, you can still use these to compute. And because they're you know, my idea was if you look at the mathematical structure correctly and you write down approximations that respect the mathematical structure, you have some chance of having something useful. That's it. Thank you.
Thank you very much.